James consumed two goods, potato chips and soda, which cost $4 per bag and $1 per can, respectively. His income is $50 and he has the following utility function. Here first, we need to find the marginal utility with respect to x and y, and then use the following relationship to find the solution to the utility maximization problem. Notice that this relationship comes from the optimal solution for a utility maximization, in which the marginal rate of substitution, which is the slope of the indifference curve, is the ratio between the marginal utility with respect to x divided by the marginal utility with respect to y. And that is equals to the ratio of the prices, which comes as a consequence of the slope of the budget constraint. So here we will solve first using the property of the utility problems, and then we will solve the problem using the Lagrange optimization. And in both cases, we need to answer what is his optimal consumption bundle and what is his optimal utility. Here we have our utility maximization problem, in which we have the utility function subject to an income constraint, where x is chips and y is soda. The price of x is $4 per bag and the price of soda is $1 per can, and we have $50 to spend. First, our task is to solve it by using the marginal rate of substitution, which is marginal utility of x divided by marginal utility of y, and that must be equals to the ratio of prices. So here we have that the utility is x to the 0.8, y to the 0.2. To obtain the marginal utility with respect to x, we simply take the derivative of the utility with respect to x. Here the constant part will be y to the 0.2, and then we take the derivative of x to the 0.8 with respect to x. So this is 0.8 times x to the minus 0.2. Now let's solve for the marginal utility of y. This is the derivative of the utility with respect to y. So here the constant part is x to the 0.8 times the derivative of y, which is 0.2 y to the minus 0.8. This means that the marginal rate of substitution is simply the ratio between the two. So here we can simplify a little bit. Notice that for the case of x, we have the exponent of minus 0.2, and in the denominator we have 0.8. If we move it to the numerator, it goes to the opposite sign. Then y is elevated to the 0.2. Again, we can move the y that is in the denominator by changing the sign, which is plus 0.8. And now, notice here that 0.8 divided by 0.2 is 4. In other words, this is our marginal rate of substitution. This is 4, and this is x to the minus 1 y. And this has to be equals to the ratio of prices. Here the price of x was 4 and the price of y was 1. So this means that this and this cancels out. And we have y x to the minus 1 is 1 over x, and this is equals to 1. In other words, x and y are equal. And then to solve this problem, we use this relationship in the budget constraint. So here we will have 4x plus y equals 50. But x is equals to y, so we can replace, if this is equals to x, this means that we have 5x equals 50, which means that x is equals to 10 and y is also equals to 10. Therefore, we have our optimal consumption bundle. And then we need to replace it to obtain the utility, the optimal utility. So here we have 10 to the 0.8 times 10 to the 0.2. And as you can see here, this is same base. So the exponents are summed or added, and 0.8 plus 0.2 is 1. So this means that the optimal utility for this problem was equals to 10. Now let's do this problem using the Lagrange optimization. Notice that again, in order to use the restriction, we need to have 0 on the left hand side. And to do that, we subtract 4x from both sides and y from both sides. So we will have 50 minus 4x minus y. So first, we need to set up the Lagrange. And here we put the objective function, which is the utility, minus lambda times the restriction, which is 50 minus 4x minus y. So this means that the Lagrange has three variables, x, y, and lambda. And then next, we take the first order conditions. With respect to x, this is 0.8 x to the minus 0.2, y to the 0.2. This is because the only variable part was x to the 0.8, and y to the 0.2 was simply a constant, minus lambda times. Here the derivative with respect to x is simply minus 4, and we set this equals to 0. The derivative of the Lagrange with respect to y is, in this case, the derivative of y to the 0.2, which is 0.2 y to the minus 0.8. And then x to the 0.8 was the constant part, minus lambda times, here as you can see the derivative is simply minus 1, because that is the coefficient of y. And we have the Lagrange with respect to lambda, which is minus 1, and then times 50 minus 4x minus y equals to 0. From these relationships, we can find the following thing. So here we notice that we will have 0.8 x to the minus 0.2, y to the 0.2 equals to minus 4 lambda, and here we have 0.2 x to the 0.8, y to the minus 0.8 equals minus lambda. And here we obtained 50 is equals to 4x plus y. If you notice here, this is actually the marginal utility of x, and then this one is the marginal utility of y. Then 4 is the price of x and 1 was the price of y. So indirectly, the Lagrange function gives you that relationship. So let's divide these two in the next page. So let's start by dividing these two. The equation 1 divided by the equation 2. So here we see that the negatives disappear and the lambda. Then notice that 0.8 divided by 0.2 is 4. And then x minus 0.2 minus 0.8 is minus 1. Y 0.2 plus 0.8 is 1 equals to 4. And then this 4 cancel out. And this means that y over x is equals to 1. In other words, y is equals to x. And we replace it in the third equation. So this is 50 equals 4x plus x. In other words, x is equals to 10, which is equals to y. And finally, we calculate the optimal utility by replacing the values of x and y. So this is going to be 10 to the 0.8, 10 to the 0.2. And when you do that multiplication, you obtain that the optimal utility is equals to 10. And as you can see here, the utility and the consumption bundle were the same by using either the Lagrange optimization or the relationship of the marginal rate of substitution equals to the ratio of the prices.